Okay, so today we're going to be going through the monotone convergence theorem. Okay, so the word theorem might sound pretty scary, but we don't need to know how to prove it. We're just going to be using it to prove the convergence of sequences. So in the previous lecture, we looked at what a sequence is and whether that sequence is convergent, divergent, alternating, and so on. Okay, and we used the limit to show if it is convergent or not. So with the monotone convergence theorem, it's a way to determine if a sequence is convergent without taking the limit. Okay, so that's what we're going to be using it as. It's just a tool that we're going to use to determine if a sequence is convergent or not without using the limit. Okay, so there's a few things we need to get through before we get to the theorem. A couple definitions. So the first definition is that of an increasing sequence or a decreasing sequence. So a sequence AN is called increasing if, okay, so that's just the definition of what that means. If AN is less than or equal to AN plus 1 for all n being natural numbers. So what this means is at any point in the sequence, the next term is always bigger than the previous. So the n plus 1 term is always bigger than n. And this is true for all n. So we have this constant increasing sequence. Okay, here it's less than or equal to, so it could be equal. So you could have terms next to each other that are equal. Overall, it's still increasing. If we replace the less than or equal to with just, the greater than or equal to with just a greater than, then we say it's strictly increasing. So here, if we have just greater than, we say it is strictly increasing. Okay, so that's just some terminology with that. Okay, so that's increasing, and then decreasing is fairly similar. So a sequence AN is called decreasing if, and I'm sure you can guess what that's going to be like, we have AN plus 1 is less than or equal to AN. And again, for all our natural numbers. So here, the next term is smaller than or equal to the previous term. And again, we could replace this with a just greater than sign. And then here we have strictly decreasing. So if we use that symbol, then it means that those consecutive ones can't be equal to. So it's either bigger or smaller, it can't be equal to, then we say strictly. Okay, so let's look at an example of this. Okay, so there's two methods that I'll show you to show if something is increasing or decreasing. If you have another method to show it, that's perfectly fine as well. Just make sure that the math works out. So here we have a sequence AN, and it's given by n over n plus 1. Okay, now just to see if it's increasing or decreasing, we should substitute some values. So if n equals 1, we have 1 over 2. If n equals 2, we're going to have 2 over 3. Then we're going to have 3 over 4, dot, dot, dot. Okay, it looks like it's getting bigger. Okay, so as n gets bigger, it looks like these terms are getting closer and closer to 1. Okay, so we have an idea that this should be increasing. Now, just substituting a few terms isn't enough. We need to prove that it's increasing. But since we have the idea, it's pretty easy to show. Okay, so I'll show you the first method. So what we can do is find AN plus 1. So that's going to be n plus 1 over n plus 2. So wherever you have an n, you just put n plus 1. What we can do now is take the ratio AN over AN plus 1. Okay, and then this ratio will tell us if our sequence is increasing or decreasing. depending on if this ratio is less than 1 or bigger than 1. Okay, and we'll see that now. So here an, that's our original n over n plus 1. Okay, divided by an plus 1. But if we divide by a fraction, that's the same thing as multiplying by the reciprocal. So we can have n plus 2 over n plus 1. Okay, so I've just taken the reciprocal because I'm dividing by that fraction. Okay, we can neaten this up a bit. So in the top, we're going to get n squared plus 2n. And in the bottom, it's just n plus 1 squared. So we end up with n squared plus 2n plus 2. So we see that the top and the bottom are almost the same, except the bottom has an extra plus 2. So that means the denominator is bigger than the numerator. If the denominator is bigger than the numerator, then the fraction is less than 1. Okay. So here we have an over an plus 1. Sorry? Oh, sorry, plus 1, yeah, you're right. Sure, just give me your student number at the end, I'll give you some points for that. Yeah, plus 1, yeah, good. But the idea is the same, so it's still bigger. So it's bigger by 1, but it's still bigger. Okay, so again, it's less than 1. So what we have is an over an plus 1, that's what we had at the beginning, is less than 1. But we can just multiply both sides by that denominator. We get an is less than an plus 1. So that means the next term is bigger than the previous term, which means it's increasing. Therefore, increasing. Okay, so this is one method to show if it's increasing or decreasing. We can take the ratio of consecutive terms and check if it is less than 1 or bigger than 1. So here, if we take the ratio and it's less than 1, that means it's increasing. If it was bigger than 1, then it would be decreasing. Okay, so we can use this ratio to test if it's increasing or decreasing. Okay. The next few definitions are if a sequence is bounded. Okay, so a few definitions and then we'll get to the theorem. So a sequence an is bounded below if there exists an M1 such that, okay, if it's bounded below, it means that the sequence never goes below this point. So we have M1 is less than or equal to an for all n being a natural number. Okay, so it's bounded below. We see that M1 is the smallest that the sequence can get. So just as a little picture, we might have something like this. So the sequence may do something like this. But we see that there's this line here at m. Okay, so whatever that m may be, we see that the sequence never goes below that line. Okay, since it never goes below that line, we say that it's bounded below. And then similar for bounded above, a sequence an is bounded above. Okay, very similar to before, if there exists an M2 such that, now it's very similar to bounded below. If it's bounded above, it means that the sequence values never go above a certain point. So we have an is less than or equal to M2 for all natural numbers n. Okay, so whatever the sequence may be, it never goes above that point. We say it's bounded above. So a picture might look something like this. Okay, and then maybe it goes down to minus infinity, could do something like that. But we see that over here, we've got this value M2. It never goes above that point. Okay, so we call that an upper bound to the sequence. Okay, so we've got bounded below, we've got bounded above. If the sequence is both bounded below and bounded above, then we say it's bounded. So if the sequence is bounded below and bounded above, then we say, then we say the sequence is just bounded. Okay, so you always need to attach this bounded below or bounded above, depending on the situation. So a sequence may be bounded above, but it may not be bounded below. Or it could be bounded below, but not bounded above. Okay, so you could have those different situations. If you have both of those cases, then we say it's bounded. Okay, so we can write this as M1 is less than or equal to AN is less than or equal to M2 for all natural numbers. So here we have some lower bound, it never goes below that point, and we have some upper bound, it never goes above that point. Okay, another way to write this is that the absolute value of AN is less than or equal to some number M. Okay, so we could have a different lower bound and different upper bound, or we could just pick some number large enough such that the absolute value is between that. Okay, so just a little picture on what I mean by that. So let's say we've got a sequence, it's bounded above and below. So maybe it looks something like this. So here it's bounded above by M2, and here, let's put a different color. So it can be anywhere below, it doesn't have to be right below the sequence. So here, that's perfectly fine, M1. So we see that the sequence is above the M1 line and below the M2 line. Okay, so we've got a different upper bound and different lower bound. Now, it doesn't matter what the upper bound is, as long as it is an upper bound. Same thing for the lower bound. So what we could do instead is just have one value. So we have one value M, let's say over there. So that's positive M above, and we can have negative M below. So that's positive M and negative M. And we see that this value of M is big enough so that the entire sequence lies between minus M and plus M. That's exactly what we have here. So this is equivalent to minus M is less than or equal to AN is less than or equal to M. Okay. As long as we have some M that's big enough so that the sequence lies between the two values, then we say it's bounded. So you can either find one value so that it's sandwiched between that, or we can find two different values. So maybe you find an M1 first to show that it's bounded below, then you find an M2 to show that it's bounded above. That's perfectly fine as well. Okay, so you can have two different bounds, so a different lower bound, a different upper bound, or you can have one that's big enough to cover both of them. Okay, any questions on that? Okay, so just as an example, okay, let's say AN is equal to sine of n. Okay, we know this is bounded from our trig functions. So what we can do is we can say that there's an upper bound of plus 1. Okay, we know that it never goes above plus 1. We can also say there's a lower bound of minus 2. Yeah. So we know that the sine function never goes below minus 1. If it doesn't go below minus 1, then it certainly doesn't go below minus 2. So minus 2 can be a lower bound. We can also have minus 3. That's perfectly fine as a lower bound as well. Okay, or we can say that the absolute value of AN is less than or equal to 3. Because we know that minus 3 is less than or equal to sine of n less than or equal to 3. Okay. So, coming up with these bounds, that's up to you. You can do it individually, so you can find a separate upper bound and separate lower bound, or you can find one that covers both. Okay, so that's up to you to do. Okay, any questions on that? Yes? Yeah, as long as it's smaller. So we know sign doesn't go below -1. So you can put -1, you can put -2, you can put -50. All of those values are lower bounds. Okay. Okay, let's look at another example of this. So an is equal to 4 minus 3n over n squared. Okay, so something like this. So the first thing that we should do is write out a couple terms to see what the behavior is like. So we can get a1, just plugging that in, is 1. a2, that's -1/2. a3, that's minus 0.56. a4, it's minus 0.5. a5, that's minus 0.44. And then it gets bigger from there. So you can add more terms to see what the behavior is like, but a few of them will give you a good idea of what the sequence is doing. So we see here, none of these are going to be bigger than 1. Okay, see, it starts out at 1, it decreases and then gets bigger. But if you add more terms, you'll see that after a certain point, it doesn't go above 0 again. Okay, so we see that 1, that could be an upper bound. And then a lower bound, we see from this list that this a3 is the smallest value. So we can have -1 as a lower bound. That's smaller. You can have -2 as a lower bound, -3. Right, that's up to you. Okay, but you just need to show that it is a lower bound or upper bound. Okay, so possible upper bounds. Okay, so we see 1, that's the biggest on this list, so that's a possible upper bound. 2, 3, you can put 10, anything like that. Okay, those are possible upper bounds. Okay, possible lower bounds. Okay, so we see that minus 0.56, that looks like the smallest in this list. Again, if you add more terms, you'll see that it is. But we could put -1, -2, -50 if you want. Anything like that, those are lower bounds. It will never get smaller than that value. Okay, but we need to prove that. We can't just write it down. Okay, so to show that it's bounded above, what we can do, so to show it's bounded above, okay, so we need to come up with some inequality that shows that the sequence here is less than some constant. Okay, if we show that, then it's bounded above. Okay, so first notice that 4 minus 3n is less than or equal to n squared. Okay, so quickly just sub in some values to see. If we substitute 1, the left-hand side is going to be 4 minus 3, that's 1. The right-hand side will be 1, so that works. Anything bigger, and this left-hand side becomes negative, but the right-hand side stays positive. So we know that this is true. Okay, what we can do next is divide through by n squared. So we get 4 minus 3n divided by n squared is less than or equal to 1. Right, we just divide both sides. So look at the left-hand side. That's our sequence that we've got. We've got 4 minus 3n over n squared. Here, 4 minus 3 over n squared. Therefore, our sequence elements, whatever they may be, any n, is less than or equal to 1. But that's the definition to be bounded above. We have our sequence, an, is less than or equal to some constant, so it's bounded above. Yeah, so that's all you need to show. You need to show that your sequence element there is less than or equal to some constant, and you've shown that it's bounded above. Okay, what about bounded below? This is also bounded below, so we can do that. Again, notice that n squared is always bigger than or equal to n. Okay, that's quite obvious. If you substitute 1, they're equal. If you substitute 2, we have 4 bigger than or equal to 2. Anything else on the left-hand side will be bigger. Okay, so why did I choose these values? Well, our n squared, that's going to take the role of the denominator, and this n, that's going to be in the numerator. Okay, so since we have n squared in the denominator and n in the numerator, this is a good starting point. Okay, now n squared is in the denominator, so we need to take the reciprocal on both sides. So 1 over n squared is no longer bigger than n, it is less than or equal to 1 over n. Okay, now we can multiply both sides by minus 3n. So minus 3n over n squared is greater than or equal to minus 3n over n, but that's just minus 3. Okay, so almost there. We have minus 3, sorry, that's n squared. N squared. So minus 3n over n squared is greater than or equal to minus 3. Okay, good. Now, if we look at this numerator, if I add something to the numerator, it's going to become bigger, right? If I have any fraction and I make the numerator bigger, then the whole fraction becomes bigger. So what I'm going to do is add 4 to the numerator. If I add 4 to the numerator, it makes it bigger. So 4 minus 3n over n squared is now bigger than minus 3n over n squared, which we said was bigger than minus 3. Okay, now look at the extreme left and the extreme right. On the extreme left, we've got our an that we wanted. And this is bigger than or equal to. On the extreme right, we have a constant, minus 3. And that's the definition of being bounded below. We have any element an is bigger than or equal to some constant, so that means it's bounded below. Now this could be minus 4, could be minus 5. Anything below that, that's still a lower bound. So here it is, bounded below. Okay, so the whole idea is to start off somewhere where we know it's true. For example, n squared is greater than or equal to n, and then work our way so that this left-hand side here becomes our an. Okay, and then the right-hand side should be a constant. Whatever that constant is, that becomes our lower bound. Okay, so it is bounded above, we showed that, and it's bounded below. So bounded above and bounded below. Therefore, it is bounded. Okay. So the question in a test or something may ask, show that the sequence is bounded. If it just says show that it's bounded, you need to show that it's bounded above and bounded below. Okay, because we need both of those parts. If the question says just show that it's bounded above, then you only show the one part. Okay, so depending on what's asked, you may have to do one of these steps or both of them. Okay, so again, if it's bounded, you need to show bounded above and bounded below. All right, any questions on this? Okay, so please go through your inequalities if you need to. This will come up quite a bit. So inequalities, manipulating inequalities. For example, in this line over here, if I add something to the numerator, you should know it makes the fraction bigger. If I add something to the denominator, you should know it makes the fraction smaller. Okay, and that will affect our inequalities as we go along. Okay, that is used quite a lot. adding things to the numerator or adding things to the denominator, that is one of the tools that we use when doing these inequalities. Okay, so it's very important that you know that. Okay, so that's all the background that we need to know for this theorem, and that is the monotone convergence theorem. Okay, so like I said at the beginning, the monotone convergence theorem allows us to show that a sequence converges without evaluating the limit. Okay, so it's another method that you can use. So if I give you a sequence and I ask, is this convergent? You can either use the limit, or maybe the limit is very difficult, and so you can use this instead. Okay, so it's two ways of showing if a sequence converges or not. Okay, so sometimes this is easier than using the limit. Okay, so this comes in two parts. So if an is increasing and bounded above. Okay, so it's increasing, it's going up, but it never goes past some upper bound. So if it never goes past an upper bound, it must level off at some point. And that's true, then it is convergent. Okay, so no need for any limits. So just a little picture of what's going on here. We can see from the beginning part, it must be increasing and bounded above. So let's put an upper bound here, let's call it M. It's an upper bound and it's increasing, so let's draw in an increasing sequence. So it must look something like that. It's increasing, but it never goes past M. If it is increasing and never goes past M, it must eventually converge to some point. Okay, so it may converge to M, it may converge to something below M, but either way it converges. Okay, so please just note that this M is not the limit value, it's just an upper bound. So it might converge to M, it might converge to something less than M. We can't be sure, but we know it does converge. Okay, so that's the first part. And then for the second part, if an is decreasing and bounded below, then it is convergent as well. Okay, the picture is very similar to before. So we have our sequence and some lower bound. Let's say it's over here. Okay, so it's decreasing, so it looks something like this. But it never goes below this value. Now, if it never goes below that value, it either converges to that value or converges to a value less than that. Bigger than that, so it needs to be above that point. And again, this M, that may not be the limit value. Okay, so just because we calculate this M, it doesn't mean it's the limit value. So the monotone convergence theorem, it can tell us if something converges, but it can't give us what the limit value is. If you want to know what the limit value is, you need to evaluate that limit. Okay, that we looked at last time. Okay, so again, the monotone convergence theorem can tell us if a sequence converges without using a limit, which is good, but it can't tell us what the limit value is. Okay, so there's pros and cons to it. Okay, so we don't need a limit, so that's good. However, we don't get the limit value, so that might be bad depending on the situation. So if the question asks you, determine if the sequence converges and find its limit, we can use the monotone convergence theorem to see if it converges, but it tells us nothing about the limit value. Okay, so instead of using this, you would have to use the limit from last time. Okay, so let's have an example of using this theorem. Okay, so we have an is equal to n over n squared plus 1. Okay, so we could use a limit. We know how to do that. But here we're going to use the monotone convergence theorem. Okay, so we're just interested if it is convergent. We're not interested in what the limit value is. Okay, so let's write out a couple terms to see if it's increasing or decreasing. Remember, it has to be one of those two to use the theorem. So A1, that's just going to be a half. A2, that's going to be 2 fifths. A3, that's going to be 3/10, and so on. And if we just notice the pattern, we see that this denominator is getting much bigger than the numerator as we go along. So in the end, we expect this to go to 0. Okay, so we expect it to converge to 0, but let's show that using the theorem. Okay, so first, we know it's decreasing, so let's try and show that. Now, we can either use that method that we had at the beginning. We find the ratio and see if the ratio is less than 1 or bigger than 1. Another way is the following. So we look at an plus 1. We want to show it's decreasing, so less than an. And we want to determine if this is true or not. Okay, so we're not going to start with one side and try to get to the left-hand side. We're going to start with it as a whole and determine, is this true or not? Okay, and you'll see what I mean now. Okay, so let's substitute. If I put n plus 1, I'm going to get n plus 1 over n plus 1 squared plus the 1 is less than n over n squared plus 1. And the question is this true? Okay, if it is true, then we know that it is decreasing. So this is equivalent to, we can cross multiply. So we have n plus 1, n squared plus 1 is less than n into n plus 1 squared plus 1. Okay, so I just cross multiplied there. And we're still checking, is this true or not? This is equivalent to, we can multiply out the brackets. So we're going to get n cubed plus n squared plus 1 is less than n into n squared plus 2n plus 2. Just adding those two ones there. Okay, this is equivalent to n cubed plus n squared plus 1 is less than n cubed plus 2n squared plus 2n. Okay, so just simplifying. Now we've got an n cubed on both sides, so we can get rid of that. Okay, we'll do it step by step. So we get rid of that. Then we get n squared plus n plus 1 is less than 2n squared plus 2n. Okay, we can get rid of the n squared on the left. We can get rid of one of the n squareds on the right. So that can go, and that can go. So this is equivalent to n plus 1 is less than n squared plus 2n. Finally, we've got an n on the one side, we've got 2n on the other. We can get rid of one of them on both sides. So here we've got 1 is less than n squared plus n. Now, if we look at the right-hand side, n squared plus n, if we substitute 1, we're going to get 1 plus 1, which is 2. Anything more than 1, and the right-hand side is definitely bigger than 1. So this is true. So since that is true, and all of the previous lines were equivalent, it means our first line is also true. So this is, in fact, true. Okay, which is what we wanted to show. We wanted to show that this is, in fact, decreasing. Okay, so this is another method that you can use to show if it's increasing or decreasing. So you can use the ratio and test if it's less than 1 or bigger than 1, or we can start out with the inequality and see if it's true or false. It doesn't matter which way the inequality goes, because here it was less than, and then we showed it was true. If we get to something which is false, then we know that we need to swap that around. Okay, so it doesn't matter which way it goes, we can still determine if it's increasing or decreasing. Okay, but we know that this is decreasing. Okay, so that is the first part of our theorem that we need to go through. So it's decreasing, which means we're using that second part of the theorem. So if we have something, if we have a sequence that is decreasing and bounded below, then it's convergent. Okay, since it's decreasing, we need to show it's bounded below. So need to show that AN is bounded below. Which is very easy in our case, because remember what AN is? That's n over n squared plus 1. We see that for any natural number n, the numerator is always positive, the denominator is always positive, everything's positive, which means it is always greater than 0. So, since this is always greater than 0, 0 must be a lower bound. So it's bounded below. Okay, very easy to show. So we've shown two things now. We've shown it's decreasing, and we've shown it's bounded below, so it must be convergent. So since AN is both decreasing and bounded below, we need to show both. It must be convergent. Okay. And we didn't do any limits. So we've shown that it's convergent without taking any limits to show that. So here, this 0, that is in fact the limit value, but we can't tell that just from this. Okay. Because remember, this could be, we could write this as greater than minus 1. But that doesn't mean minus 1 is the limit. Okay, so please be careful with that. All right, any questions on this? Okay, if you're lost, please let me know. Yep. Sure. Which one? The bounded part. Oh, decreasing. So that was from here. Yeah, so we write this down. So AN plus 1 is less than AN. Remember, that was the definition. Yeah. Yeah. Oh, you can't put 0. We always start from 1. Yeah, so, yeah, no, that's a good question. So sometimes the natural numbers, we can take it starting from 0, or we can take the natural numbers starting from 1. So we're going to start from 1. Okay, yeah, so a good question there. Okay, yeah, if you do ask good questions, you can get points as well. So, and the other guy that also corrected me. Okay, can you just see me after? Okay, yeah, so just a note, I'll put that down here. When we talk about the natural numbers, we're going to start from 1. Okay, so we don't have to worry about the 0 there. Okay, any other questions? Okay, well, even if you think your question is silly, it might not be, right? So ask if you need to. Okay, So the tutorial problems are up. I just want to add a few more things to that. Okay, so this is extra for the tutorial. Okay, so this is exercise 11.1. So these questions are in the tutorial. So the tutorial just says determine if they're convergent or not. So please do it using the standard method of using the limit. But now that we know the monotone convergence theorem, can you do these ones using the theorem instead? And check your answer. So that's for number 23, number 24, 27, 34, and 47. Okay, so just those ones, try to do that using the monotone convergence theorem. Now, these ones are going to be as difficult as it gets. So those other problems there, you can use the limit to check convergence, but using the monotone convergence theorem will be more difficult. Okay, so if you can do just these ones with the monotone convergence theorem, then you should be fine. Okay. You can try the other ones as well, but that might be a bit more difficult. And then just a note for number 47. Okay, so if A is less than B, then the natural log of A is less than the natural log of B. Okay, so that's a little hint for that one. Okay, so when you're showing the inequality for increasing or decreasing, if you have A is less than B, we can take the natural log on both sides and the inequality stays the same. Okay, so that will help you out. If you do finish these before Thursday, then you can also submit them as the homework. Okay, so that will count as the tutorial problems and the homework problems for this week. Okay, but don't rush them, right? So take your time with them. You can submit all of them at once if you're quick with that, but you will have until Thursday. Okay, and with the previous homework, that is still open. So if you want to submit that homework, you can do that as well. Okay, any questions on this? Okay, just a final note for the practice test on Thursday. So the practice test for this Thursday is the same scope, the same type of questions as the class test for the following week. So you're going to do the practice test, you're going to get your results back, you can see where you did badly, and then you can use that to improve for the actual test. Okay, so you can think of it as having two chances to doing the test. Okay, so the practice test, that will count as formative marks, okay, because it's not a big main test. The class test for the following week, that will be summative marks, that's the main class test. Okay, but I'm just calling it practice class test. However, it will still be formative marks. Okay, any questions on that? Okay, so same scope, same time, all of that. So you can prepare for both of them at the same time. Okay, any questions? Okay, cool. Those two guys just see me after and you can get your points. Okay, I'll see you on Thursday.